Okay, so today we are going to move our discussion to the Gaussian splitting, which is kind of the next kind of technique about the neural rendering. So if we briefly review what we have discussed so far in this course, we basically discussed some kind of the multiple representations about 3D encoding and the decoding. So we started to discuss basically how to basically encode and decode the point cloud, and then we moved on to basically implicit representation and how effective it is in terms of like decoding some kind of 3D the shapes, 3D geometry. And then after that, we started to discuss the ideas about basically reconstructing some 3D things from the multi-view images. So we discussed some kind of basic things about the structure from motion, how we can basically estimate the camera poses from the multi-view images. And based on that, how we can do some kind of the 3D construction. So the basic idea was basically reconstructing into some kind of first point cloud based on kind of key points that we found across the multiple images. And then we extended the idea by using some kind of neural net that can also basically decode some kind of the opacity and the color information in a way that we can not just getting some kind of a point cloud, but directly enabling basically rendering into some kind of the images from the arbitrary views. So that was the basic idea for the neural rendering. So the kind of key technique that we discussed last time was basically the NeRF, the neural rendering the field, which was basically the technique which is based on the Boolean rendering the equation. Right? And the basic kind of the idea for this kind of technique was basically using the kind of graphic pipeline, basically using some kind of the rendering the framework, which is based on kind of the shooting the rays from the image planes into the 3D scenes. So here the question is that when you shoot a ray from the camera through one of the pixel in the image plane, basically how we can determine the color of the pixel by incorporating all the information about some kind of the geometry and the color defined in the 3D scenes. So basically what we defined in the 3D space for those kind of the rendering kind of thing was basically the opacity and the radiance information. So that was also the reason like why it is basically called the neural radiance field. Right? So we could see that basically the color could be determined by just taking the integral of the radiance and the opacity along the ray. And also basically this is combined with the transparency, which is also defined with some kind of the opacity information. So from the definition of the transparency here, what we could see is that the transparency was kind of like non-increasing function over basically the traversal of the ray. So it's basically starting from the 1, and basically over time, that when you basically fly over some kind of array, we could see that the transparency is basically decreasing, basically based on the definition of the transparency, as you can see in the slide like this, right? Based on the formulation defined based on in the form of the exponential terms like this, okay? So that was basically the Boolean rendering the equation, and we could see that this was quite effective compared to some kind of the modeling everything as kind of a solid object in terms of that we can update every single the point along the array. So it is also making the update through the backpropagation to be more effective, and also it is basically more the flexible representation to represent all the things defined in the 3D space. Right? So this was kind of the basic idea for the neural rendering and also the NeRF. And the things that I wanted to briefly mention is that while this looks like some kind of a very new technique, as I also mentioned last time, actually the core, the idea that has been used in the NeRF are basically very kind of the old technique that has been actually introduced like some decades ago. Not only for the volume rendering, but also for this kind of the idea about basically rendering things into the images without like specifically defining some kind of the explicit geometry has been actually quite the old ideas that especially have been explored in the 1990s. So you can see some kind of the history of this kind of the novel synthesis, which has been basically explored in terms of that, how we can do some kind of some rendering without having some kind of explicit geometry, but by defining some kind of some explicit information plus some kind of the implicit function. So as you can see, there are some kind of lots of the variants in terms of that. There are some kind of different ways that in terms of how we can parameterize the information in the 3D scene. So what we have done in the NeRF was basically having some kind of the radiance information and the opacity information. Especially the radiance information has been parameterized with the 5 the parameters, right? The X, Y, Z for the position, and also for the 2 other the parameters for the viewing direction. So that's kind of the some related with the idea about the plane objective function here. But there are also some kind of the other the ideas in terms of like, we can also parameterize everything in these things in terms of the 4 parameters like this in the limit graph. In terms of that, we are having the 2 parameters for the image pixel in the image plane, where basically everything is projected, and also for some kind of using some sort of the multi-plane representation in a way that everything in the 3D space is also defined with some kind of the multiple planes. And for each of the plane, we are also having another the 2 parameters in a way that we can see some kind of the some relationship between the pixel in the multiplane representation for each of the plane to the pixel in the image plane. And there are also some kind of the other ways in terms of like using some kind of the panoramic images and also doing some kind of projections from the panoramic images into the image plane. So there is actually a very long history in terms of that, how we can do some kind of the rendering without explicitly define some kind of the geometry in this 3D space. So you can see that actually the NeRF was one of the idea in terms of that we also define some kind of the implicit representation in terms of like, representing everything with some kind of as kind of neural network function. And we also started to discuss some kind of the hybrid representation as well in terms of like how we can also incorporate some kind of the explicit representations as well in terms of that we can achieve some kind of some better efficiency both for the training and also for the rendering as well. So one of the ideas that we discussed last time was basically instant NGP, which is basically incorporating the voxels as well in terms of that we also store some kind of some features for each of the voxel in a way that the features are basically decoded through the rendering the pipeline. So this was kind of the basic idea in terms of that we are kind of like reallocating some kind of the parameters, the neural net functions in terms of that those kind of the parameters are basically now allocated explicitly into the 3D space in a way that we can more basically see like basically which basically the parameters defined in the 3D scenes are basically associated with each of the array that we are shooting into the 3D space, right? So the thing is that when you use the NeRF pipeline, if we shoot a ray, and when you determine the color for each of the ray, all the parameters of the neural network should be basically updated based on the loss function that we are defining, right? But for those kind of cases that when you basically distribute all the features into each of the voxels in the 3D space, only the features that are basically stored in the voxels, where basically the ray is basically passing through, those features are only updated. So we can basically see some kind of more spatial, some kind of association of the features with some kind of rays that we are shooting, right? So that can be basically more effective in terms of the training and also the rendering as well. But that is also basically compromising some kind of the memory efficiency. This will basically involve some kind of the case that we are taking more the memory to store all the information. So we also discussed some kind of the ideas about how we can compress those kind of the information that we are defining in the 3D space using the multi-resolution the representation and also using the hash table the ideas for the instant NGP. And also the algebraic way to compress everything was basically using some kind of the tensor decomposition. This was also the idea that was introduced by the TensorRF, which was basically doing some kind of the decomposition of the 3D and the 4D tensors into the 1D and the 2D tensors in terms of that we are basically compressing the 3D, 4D information into the low dimensional, the low rank kind of the tensors, right? So those are some kind of the ideas in terms of how we can basically combine some explicit information and also the implicit information in terms of that, having some kind of the features defined in some kind of the voxels, and then having some kind of decoder for those kind of features, right? And not only for the voxels, but also for the points, we can do the similar thing. As I also briefly mentioned last time, what we can also do is that given some kind of some rough point cloud describing the geometry, we can also consider basically define some kind of the features for each of the point in a way that when you also do some kind of the rendering, when you shoot a ray, into this 3D space, we can also see some kind of some points that are close to those kind of ray, and basically apply the same volume rendering the equation. So this was basically another example in terms of that we can also combine the point cloud information representation with some implicit the functions in terms of that we are making some hybrid representation. And there's another example which is also now using some kind of the mesh plus some kind of features defined on the triangles of within meshes. And the idea that we are going to discuss today is the Gaussian splitting. So this is also the kind of technique which is on the line of the work in terms of making some hybrid representation, which is also kind of similar with using the point cloud plus implicit function. But now we consider basically not just defining some kind of the single point, but the point with some kind of the volume information, basically defining some kind of the 3D Gaussian blobs that are basically defining some kind of the 3D scenes. And the good thing of like using this kind of some point-based representation is that, so as I also briefly mentioned in the case of the structured different motion, from the structured from motion the pipeline, what we can achieve is not only some kind of the relative camera pose, but actually we can also achieve some kind of this sparse point cloud. But that's also what we have seen in the previous lecture, right? So when you basically find some kind of key points over the images, from the correspondences, if we shoot the ray and find when you find the intersection the point, we can basically have some kind of some 3D points for those kind of key points, which is giving some kind of sparse point cloud. So the good thing with having this kind of point-based representation is that we can utilize this kind of some sparse point clouds as some kind of some initial some kind of points. In terms of that, we can now utilize some kind of those points by augmenting those points with some kind of extra some kind of some information for this 3D. So we are going to see some kind of basic ideas for the Gaussian splitting for today. So for the Gaussian splitting, let me first play the video. Okay, I think this is the video that you have seen before. So the problem of the NeRF that we have seen last time is that it is basically taking quite a long time, not only for the training, but also for the rendering as well. Because every time we need to basically shoot a ray and basically sample the points and basically evaluate the opacity and the radiance the function, right, for all the points, and then doing some kind of the calculation based on that. So this will basically involve lots of the information, lots of the computation time also for the rendering as well. But one of the biggest the advantages of the Gaussian splitting is that it's basically super fast. I'm not sure whether you can see, but actually this is the rendering the outputs of the Gaussian splitting, which is now rendered with the speed of the 60 frames per second. So it's super fast, right? Actually, this is kind of the things that we are basically exploring the reconstructed the 3D scenes. So this is not just kind of the video that is captured directly from the real scene, but it's actually just like navigating the space. So you can see that here, at the top of the scene above here, we can see some kind of some parts that are basically remain as the black, non-reconstructed kind of areas. So yeah, it's basically just like changing the camera pose into like random kind of things. And so you can see that actually the quality is really good. It really looks like some kind of like seeing the video, while the rendering the speed is also super fast. So this is kind of this was some kind of the breakthrough that people have seen with this technique, the Gaussian splitting, which was introduced about like 2 years ago in 2023. So while we are seeing some kind of some very clear images for those kind of for in this video, actually the thing is that the scene is represented with this kind of the Gaussian blobs. So this is kind of some sort of the raw rendering the outputs without using the volume rendering equation, but just directly rendering some kind of the explicit the representation that have been used for the rendering. So those you can see that there are lots of some Gaussian, the ellipsoid, the blobs in the scenes, and these are some kind of some sort of some primitives that we are using to represent these 3D scenes. And based on those kind of primitives, those are basically defining the opacity and the radiance information that we discussed in the NeRF. And based on that, we can also use the volume rendering the equation to get some kind of the final rendered images. So when you talk about the sorry, let me just quickly play this view. So yeah, you can see that actually there are some kind of the Gaussian blobs. And interestingly, most of the blobs are basically located on the surface of the objects. So you can roughly see some kind of the what would be kind of the shape of the geometry of some kind of object in the scene, while there are also some sort of the floating some blobs in the scene as well. So those are basically representing some kind of the the opacity and the color information. So when you basically develop some of the neural rendering techniques, those might be some kind of the important some kind of factors that we want to basically achieve. So in terms of that, how we can get some kind of the accurate rendering the results. So that might be the first thing. And also the speed is quite important, right? So how we can also achieve some kind of the very fast rendering speed. And also the fast computation time for the training as well. So these are also kind of important thing. And also the memory efficiency. So while we have seen some kind of some technique that is quite fast for the rendering and also the accurate, which are like instant NGP and the tensor, the RF, those are some kind of examples for some fast rendering kind of techniques. But we also have seen that those are not that the memory efficient kind of the techniques, right? And also how much those can be easily integrated into some existing the graphics framework might be some kind of important factors that people might want to consider to develop some kind of neural rendering techniques. And the good thing of the Gaussian splatting is that it is basically achieving some kind of the good results for all those kind of 4D factors. So it's basically very accurate in terms of giving some kind of good, some realistic and clear images for the arbitrary views. And the more importantly, the Gaussian splitting is really fast, both for the rendering, it's like basically, at least like 60 frames per second, and it can be like even faster than that. And also taking not that much time for the training as well. And also it's very basically very the memory efficient, so especially compared to the instant NGP and some other techniques. Those techniques may basically take some kind of the more than like tens of the gigabyte or the hundreds of the gigabyte to just represent a single object or the scene. Compared to that, Gaussian splitting would be the much more basically efficient the techniques, not only in terms of the computation time, but also in terms of the memory as well. And this is also very good technique in terms of it can be very easily integrated into some kind of graphics framework. Actually, the reason for this is that while we have seen some kind of techniques that are basically based on the ray casting, the framework, which is basically shooting the ray for each of the pixel, actually the Gaussian splitting is a technique which is based on the rasterization. So which means that we are not just shooting the ray for all the pixels and checking the intersecting point, but it's more about basically projecting all the primitives defined in the scenes into the image plane in a way that we can basically make the computation faster. So we're gonna basically get into the ideas about basically how we can utilize the rasterization pipeline in our rendering, the Gaussian splitting based rendering framework. So this is the basic idea. And actually, if we see some kind of the basic idea for the Gaussian splitting, you can see that this is also kind of technique that is also based on some kind of some core idea which was introduced more than 20 years ago. So actually, about like 1990s, the late the 1990s and in the 2000s, there were some kind of lots of the attempts to utilize the point cloud representation for many kind of the graphics applications. So as you can see here, even there are some kind of the computer games that were attempting to basically use some kind of the point cloud based representation for some graphics, the pipelines like this. And so more importantly, what we also could see in the 2000 was that there are some kind of we start to see some kind of the 3D scanners that can actually capture some 3D objects in the scenes in a very large scale and also very fine kind of some accuracy. So this was the first the 3D scanner that was introduced in the 1999 or the 2000, as far as I remember. And this was the first case of capturing that it was able to capture this kind of the big statue which size would be like the 4 or the tens of the meters, I guess. With some kind of very the high accuracy, which can also basically, and also the very fast speed. As you can see, this was the case that we could basically capture the things while basically having more than 100 millions of the points per second. So you can see some that there are some kind of so this is not for the scanning. This is for the rendering, but for the scanners, actually we also could see that there are yeah. So this is the case, taking like 4 million the points for the entire statue. So this was basically very large scale the point cloud that people could see could acquire from these 3D scenes using the scanner. So that was happening in the 2000. And also it was like very accurate, as you can see, in the quality like this. All the fine details are captured like this. So at this time, like what people started to like think was basically how we can utilize this kind of some scanned point cloud directly for many kind of applications without doing any kind of conversion into the meshes or something. So while we are also going to discuss basically about this kind of conversion of the representations, actually there are some kind of attempts in terms of how we can directly use the point cloud for many things, especially for the rendering. So this was kind of the basic idea that people have started to discuss at this time. So actually, there are lots of some kind of techniques in terms of how we can use the point cloud directly for the rendering. But if we start to think about how we're going to use the point cloud for the other applications, for some manipulation or the many things, then we will need to convert these things into the other representations. So we're going to get back to this point after the midterm. But this was kind of the interesting idea in terms of how we're going to directly render the point cloud into the images. And actually, if you find some kind of the old materials like this, actually more than 20 years ago, there was some kind of even some kind of the conference for the older research about how we can do some kind of point-based rendering and how point-based some kind of graphics pipelines. So you can check out lots of some kind of materials at this time. So even there was some kind of the whole community, research community about how we can directly use the point cloud for the rendering. But after trying all the things, like people realized that actually for the efficiency, it's better to convert into the meshes, and then there are some kind of some follow-up the conversion that works. But anyway, so this was kind of the basic motivation at this time in terms of how we're gonna directly use the points for the rendering the pipeline. And then the Gaussian splitting is actually nothing, but just directly utilizing the idea that has been introduced at this time based on the points that we could achieve with the structure promotion. So at this time, like some kind of the basic idea was basically using introducing some notion of the surfel, which is kind of the short name of the surface the element. So here the basic thing is that now we are seeing each of the point as some kind of not just kind of the single point in the scene, but as some kind of the surface the element, which is encoding some kind of the basic information about the 3D geometry. So now what we can see is that each of the surfel is not only defining the position and also the color, but if we really just see the point as just kind of point in the 3D scene, then we need to somehow interpolate those information to define the surface, right? So we are not just seeing the point as some kind of the point, but just like associating some kind of the area information. So in terms of that, basically one kind of the idea was basically seeing each of the point as kind of the disk, very small disk, which now have some kind of area information and also the surface normal information as well. So basically when you see each of the point as kind of the disk, so the question is that how we can effectively do some kind of the rendering with the tones of the disk that we have in the 3D space. So this was basically the idea that has been discussed with the name of the surfel. And then after that, people also started to extend this idea, not just having some kind of the disk in the 3D space, but also basically define some kind of some kind of volume in the space. So which is basically just treating each of the point, assigning some kind of the volume information for each of the point. In terms of that, now we can treat each of the point as some kind of the Gaussian block. So then this is kind of the case that now we can also consider using some kind of the volume rendering the equation for the rendering. That is basically the equation that we have seen that in NeRF case. And especially for the good thing of like having this kind of representation is that for the multi-view to 3D reconstruction in the case, Now we can consider using some kind of this first point cloud that we are achieving with the multi-view images as some kind of the initial, this kind of the some volume splat. So we are starting from this kind of the volume splat and doing some kind of the some refinement in terms of that defining all the 3D geometry with some kind of the Gaussian blobs, and also using the volume rendering equation for the rendering. So this was the basic idea that actually has been introduced in the 2001, and it's basically revisited recently with the name of the Gaussian split. What are splits? So splits are basically this kind of some Gaussian blobs or some kind of the disk in the 3D space, some kind of the basic primitives that we are saying in this context. Okay. So actually, either we can consider the points as some kind of the disk, or consider the points as some kind of the Gaussian blobs. And what we are going to discuss today is about basically when you have some kind of the volume split, when you treat each of the points as kind of some Gaussian blobs. But while this idea also can be extended to the case of that when you treat that points as kind of the disks as well. So how to define the size of this split? So it depends. So actually, in the context of this kind of old work, we could basically consider define some size of the split based on the density of the points that we have. But in the newer rendering, the context, actually we can consider basically optimizing this kind of the size of the split over time through the volume rendering the equation, the loss function, and the backpropagation. But basically, what we are defining as some kind of the basic the attributes for the surface split and the volume split is that for the surface split, the case we will need to basically define the position and the surface normal information, and also the radiance information, right? And also the color information as well. But for the volume rendering the case, now we are basically defining the position, but not the normal, but basically the covariance the matrix, which is defining some kind of the size and the orientation of that the volume. And we also need to have the color information as well. So you can say that this is kind of the more explicit some representations of the opacity and the color, the kind of things, not just using the neural net. So this is the case that we are using some more like explicit representation for the volume rendering. Any questions on this? So what we are going to briefly see for today is not about exactly about how we can do some kind of a training of the things we did the Gaussian splitting the pipeline, but actually we are going to talk about some kind of the old technique in terms of the how we can do really some kind of volume rendering with the set of the volume displays, and what we kind of some basic the machineries that we can use for those kind of the volume rendering with displays. Okay. And for more details here, I strongly recommend you to check out this paper, which was published in 2002. So it's kind of, you can say that this is very old work. And interestingly, this old work has been revisited very recently with context of linear rendering, and which now is becoming more standard technique for many kind of the image to 3D construction. So basically, what we are going to do is that we're going to see is that we are going to assume that all the 3D scene is now represented as some kind of a set of some volume split, which is basically having these kind of two properties, like opacity and the radiance. So these are really some kind of two properties that we discussed for the NeRF, right? So exactly the same. So to simplify the discussion for the today's lecture, we are going to assume that the split is now having the color information instead of the radiance information. So this is like not the view, the dependent, just the color for every view. But all the things that we are discussing for today can be directly extended to the radiance as well. So there's no big difference here. But the thing is that we are also additionally defining some kind of some Gaussian corner, the ellipsoidal Gaussian corner in the 3D space, which is also now defined with the center point P here, and also the covariance the matrix, which should be symmetric, the 3x3 matrix. Okay. So given this kind of the center and the covariance, this is basically nothing but we are defining some kind of the Gaussian function in the 3D space, and the Gaussian function in the 3D space will be defined in this form. Okay. So based on the Gaussian corner and the opacity and the color information, we're gonna be determine the opacity and the color for any arbitrary point in this 3D scene, and then we're gonna do some kind of the compute the Boltzmann equation. But we're gonna see how we can very efficiently compute the Boltzmann equation with some kind of the approximation and the assumptions. Okay. And before we get into actually how we can exactly compute the Boltzmann equation, we are going to get into slightly more details about the graphics the pipeline in terms of the coordinate system. So we have discussed the coordinate system a bit last time, but actually in the graphics pipeline, we can also consider some kind of the coordinate system, which is including like object coordinate system and camera coordinates and also the ray coordinates. Actually, there are something more. Actually, we can also consider some kind of the world coordinate system in between object and the camera here. And also, instead of the ray coordinates, we can consider some kind of the screen coordinate system based on the image plane with some kind of scaling and the shift term. But let me skip some details here. If we only consider those kind of three coordinate system, the meaning of like each of the coordinate system is that, for example, for the object coordinates, this is basically nothing but some kind of local coordinate system for each of the object. And the object that we are defining here is the split, the volume split, right? So we can basically assume that each of the volume split has its own the local coordinate system. Obviously, the origin of the coordinate system will be the center of the Gaussian split. And also the axis of the coordinate system are also aligned with some kind of the principal directions of the ellipsoid. So this is kind of the way that we are defining some kind of the object coordinate system. So once we basically define the object coordinate system for each of the Gaussian split, now we can also define some kind of some sort of scene the coordinate system, which is defined based on the camera parameters, right? So once we basically define the extrinsic parameters of the camera, based on that, we can define the camera coordinate system. And then the transformation from the object coordinates to the camera coordinates can be defined with some kind of the rotation and the translation, right? Then we're gonna call the transformation from the object to the camera coordinates as the viewing transformation, which will be defined based on the rotation and the translation. So by the way, some of the terms that we are using here may not be some typical terms that are used in the many graphics pipelines, but those might be some of the terms might be some special terms that are only used in that the old paper in 2002. So there might be some confusion in terms of which basically the coordinate system is like corresponding to the coordinate system, the typical the graphics pipelines, but we're gonna follow the terms using the paper. Otherwise, so that you can also basically check out some more details in the paper if you want to see. So basically, we're gonna use the terms of the viewing the transformation, which is converting from the object coordinates into the camera coordinates, and this will be basically some kind of some rigid body transformation, rotation, the translation. And as we also have seen in the camera, the model kind of the lecture, we can also consider some kind of the projection, right? So we're gonna say some kind of the ray coordinate system, which is basically defined based on the intrinsic parameters of the camera, but without considering any kind of the camera parameters like focal length, all the things. We're gonna say that the ray coordinates is basically nothing but just directly projecting all the 3D things into the image plane with this kind of the projected transformation. So here the projected transformation is basically nothing but just like directly dividing each of the x, y, the coordinates by with the z-axis here. And so this is basically the projection, right, from the 3D to the 2D. But we are introducing the third coordinate here, which is basically the depth information along the depth. So this is some kind of specific way, like in terms of how we define the ray coordinates, as kind of like making simple the projection from the 3D to 2D, which is the case that the focal length becomes 1, right? So it's simply dividing each of the XY coordinates by the Z coordinates, and just like here, the only thing is that we are taking the distance into the ray, the depth information as kind of the third coordinates here. So then here, what we can see is that when you shoot some kind of the multiple rays from the center of the camera here into the 3D space, while basically we are shooting the rays in this form with some kind of the lines you can see here, when you convert all the rays into the ray coordinate system, what we can see is that all those kind of rays become some kind of the parallel lines in the space, while we are still having some kind of the third coordinates, which is basically describing the distance over the ray. So the first two is basically the projection into 2D the space, and the last term basically becomes the distance here. So we are basically defining this kind of the three coordinate system. So we're gonna use this kind of notation. The x indicates the object coordinates points, and x prime is indicating the camera coordinates, and the double prime is indicating the ray coordinates. And for each of the coordinate system, we are having the viewing transformation and also the projective transformation. Make sense? And the viewing transformation will be also will be denoted as the function f here, and the project transformation will be denoted as the function g here. So we are basically having a bunch of some kind of transformation, and then we're gonna basically compute the volume rendering equation in the ray coordinate system after doing all the conversion. So this is kind of the basic idea about the coordinate system we are going to use. And the thing is that we are basically assuming that for all the ellipsoidal, the Gaussian, the corners, all these kind of the center and the covariance matrix, those information are basically defined in the object coordinate system. So we are first defining the ellipsoidal, the corner in the object coordinate system, and we're gonna see how those kind of the corners are also transformed through the viewing transformation and also the projective transformation. So basically, define the Gaussian corner with the object coordinate system basically means that by definition of the object coordinates, basically the origin of the center of the Gaussian corner will be defined at the origin of the object coordinate system, and we're going to also assume that all the corners are basically defined with the axis aligned the covariance matrix in the object coordinate system. Which means that in the object coordinate system, the 3x3 matrix for the covariance matrix will be the diagonal the matrix, only having some kind of the scaling, scale term for each of the principal directions, right? So this is kind of the case. So once we have those kind of setup, what we are going to see is that how is each of the Gaussian, the kernel will be basically transformed through the viewing transformation and the projective transformation. So here the question is that will a Gaussian kernel defined in the object coordinates system remain still as the Gaussian kernel after applying the viewing transformation? Or what's the answer for this? Yes or no? So yeah, let's see step by step. So what we can see is that the viewing transformation will be some kind of linear transformation. Basically, it's a Ricks-Budd transformation which is involving rotation and the translation, right? So for the cases that when you have the viewing transformation like this, which is basically involving some linear part here, which will be typically rotation, and also the translation part here. Basically, each of the object coordinate will be basically converted into camera coordinates with this kind of function, right? And we can also consider having some inverse function like this. So you can see that this viewing transformation is basically a linear transformation. So from this, I would like to ask you some kind of some hands-on work from some kind of some math, some calculation. So given that when we define the ellipsoidal the Gaussian corner in this way, so let me just like define these two terms. So let me define this like P prime and the V prime are basically having this kind of the terms. So obviously you can see that this will be some kind of some transformed the point and the variance in the camera coordinates, right? So I'm giving you some kind of the information for this. actually in the camera coordinates, the center of the Gaussian, the corner will be this P prime defined like this, and also the variance will be defined as kind of the form of the V prime. So given that, can you rewrite the Gaussian corner in the camera coordinates as the function of the Gaussian corner defined in the object coordinates? So what actually I recommend you to is to basically to do the opposite first. So whether we can represent the Gaussian corner in the defined in the object coordinates as kind of the function of the Gaussian corner defined in the camera coordinates. So try to basically rewrite the Gaussian corner defined in the objective coordinates as kind of Gaussian corner in the camera coordinate like in this form, based on the definitions of the P prime and the B prime and the Gaussian corner here. I'm gonna give you 5 minutes for this. Okay, 5 minutes might be too long. Okay, 3 minutes. So if you need more time, I recommend you to check this out after the lecture. But since we are running a little bit out of time, so if we see some kind of details in terms of like how we can see the relationship between these two, let me first do the opposite in terms of like rewriting the Gaussian corner defined in the object coordinates with the Gaussian corner defined in the camera coordinates. Then this is the definition of the Gaussian corner. And we can simply rewrite some of the terms here in terms of we are replacing x and p here like this. And then the translation part will be canceled out. Then we're gonna have this equation. And we're also rewriting this equation by just taking out the linear part here in terms of having this part, right? So from this equation, what we can see is that now this becomes some kind of the variance term in the camera coordinates like this, right? So by defining the V prime, as we have seen in the previous slide here, by taking this V prime here, we can now rewrite the whole equation in this way. Then we can see that when you take the V prime in the here, then we can take we are seeing that this becomes the same that we are taking the Gaussian corner in the camera coordinates multiplied by the determinant of the linear part of the viewing the transformation. From this kind of the derivation, what we can see is that actually the Gaussian corner defined in the object coordinates, like when you convert that, when you see that the corner from the camera coordinates, still the corner remains as the Gaussian corner, while it looks like we are applying some kind of the rotation and the scaling, right? So the scaling term can be seen here. So how can you see how can you see that the Gaussian corner looks like the rotated in the camera coordinates? So the rotation is kind of like involved in the new definition of the covariance here, right? So we are multiplying the linear part in the before after of the covariance matrix, right? That is basically showing that actually the Gaussian corner, which has been seen from the camera coordinates, looks like we are basically rotating and scaling the Gaussian corner, right? But still, it remains as some kind of the Gaussian corner in the 3D space. Make sense? Any questions on this? So yeah, this is kind of good thing. So the Gaussian corner in the object coordinates is also another the Gaussian corner in the camera coordinates. But how about the case that when you apply some kind of the projective the transformation? So will a Gaussian corner defined in the object coordinates will remain in the Gaussian corner in the ray coordinates? The answer is no, because this is the projective transformation. So we will be able to easily find some kind of example that the Gaussian corner does not remain as the Gaussian corner in the after applying some projection. But what we are going to do is that for basically making the computation simpler after in the volume rendering the equation, we are going to see how we can basically approximate the projective transformation as kind of some linear transformation. in a way that we can still treat the Gaussian corner in the ray coordinate system as the Gaussian corner as well. So that's kind of the basic idea for the Gaussian splitting. And how we can do some kind of the approximation of the project transformation as the linear function. What's the kind of the closest some linearity transformation that best approximates the project transformation. So what we are going to do is that we are going to use the first order the Taylor expansion, which is the approximating the transformation, especially at the center of the Gaussian split, the P prime here. And how we can apply the first order the Taylor expansion. So I'm not sure how many of you are familiar with the Taylor expansion, but the Taylor expansion is basically defined in this way, right? By defining some kind of the Jacobian term here, we can now approximate the projection function here, which is defined as the G function here, as some kind of the first linear function like this. So we have seen this like what's the projection function, right? The projection function was basically nothing but just like dividing xy coordinates by the g coordinates. So let me just go back to here. So this was the g function, the projection function, just dividing xy with the g coordinates here, and just taking the distance along the ray, the norm of the x-prime coordinate here as the third coordinate, right? So since this function is not a linear function, we are going to take the Jacobian for this function in a way that we can do some kind of the linear approximation. So given the definition of the projection here, how we can compute the Jacobian here? What do we get once we get compute the Jacobian here? Can you quickly do some kind of calculation with this? So you can check out this math, but you will see that actually this is nothing but we have seen how we define this g function as the projection, nothing but just dividing x by the z, dividing y by z, and just taking the distance along the ray, taking the norm of the ray, just taking the gradient for each of the x, y, z coordinates of the output of the g function with respect to the x, y, z coordinates of the input vector, right? And then just taking the 3x3 matrix with that. And you can see that actually this is nothing but we are having this form, right? So nothing but just like taking the gradient of the x1 by x3 with respect to the x1, right? Then we get this. The same thing, taking the gradient of the x1 by x3, the x1 over x3 by the x2, then we're going to with 0, just like taking this. So you can see that actually the Jacobian can be easily calculated from our definition for the projection, the function in this way, right? So by just having this kind of some Taylor expansion, what we can see is that now by calculating the Jacobian matrix, we can basically approximate given the projection function as kind of some linear function. So now we are simplifying the notation for the Jacobian as the J simply here. And then the translation part can be calculated in this way. So which means that when you approximate the projected transformation into the linear function, then with this kind of approximation, the Gaussian corner defined in the camera coordinates will be also seen as kind of another Gaussian corner in the ray coordinates, right? So exactly the Gaussian corner in the camera coordinates will not be Gaussian in the ray coordinate system, but if we do some kind of the linear approximation for the projection, then we can treat the Gaussian will be also remain as the Gaussian, right, after the transformation. So what you can see is that, so given that the double prime, the center in the ray, center of the Gaussian in the ray coordinate system is defined in this way, and also the variance of the Gaussian corner in the ray coordinates is defined in this way. We can also see that the Gaussian corner in the ray coordinates can be also written with respect to the Gaussian corner in the camera coordinates, as we have done in the previous slide. It's basically the same thing because everything is the same, the linear transformation, right? So given this kind of the two sequential linear transformation, now what we can do is that we can rewrite the Gaussian corner in the ray coordinates as the Gaussian corner, which is originally defined in the object coordinates, right? So once we basically define the Gaussian corner at the center of each of the object coordinates and also some axis-aligned variance based on the two transformation and also with the linear approximation for the projective transformation, now we can simply derive the Gaussian corner, the same the Gaussian corner, but which is now defined in the ray coordinate system. Okay. And the Gaussian corner defined in the ray coordinate system will be basically nothing but basically applying some, it will look like some kind of applying some kind of rotation and also the scaling term in the original the Gaussian corner in the object, the coordinate system. The scaling term is defined in this way with some kind of determinant of the linear term in the Buing transformation. And also what we can see is that typically, obviously, the linear term in the Buing transformation will be rotation, right? And the determinant of the rotation matrix will be 1. Actually, the determinant W will be 1 for most of the cases. And we will just need to compute the determinant of the J here. Right? And this is kind of some approximation. Obviously, the Gaussian corner will not be Gaussian in the ray coordinate system, but this can be one way that we can simply basically approximate the Gaussian corner as the Gaussian in the ray coordinate system. This can be calculated this way. So we know how we can calculate the P double prime and the V double prime, which will be defined in this way, right? So once you basically, so given the P and the V defined in the object coordinate system, you calculate the P prime, P tau prime, and the V, the tau prime here, sorry, which is now defined in the ray coordinate system. And then basically also calculating the Jacobian term in terms of like that we determine the scaling term as well. So then it becomes that we are seeing some kind of the conversion of the coordinate system. So seeing the same the Gaussian corners, but now defined in the ray coordinate system. Okay. So this is like more about basically how we do some kind of the conversion of the coordinate system for the Gaussian corners that we define in the object coordinates. Then based on that, how we can do some kind of the calculation of the volume rendering the equation. So if we see the volume rendering equation again, it was basically defined in this way, basically taking the integral of the multiplication of the color here, it can be radiance if we have some parameters for the view direction as well. And also the opacity, which is also called the extinction coefficient, and also the transparency, which is defined based on the opacity here. But what we are going to do is that we are going to calculate this equation not through the ray casting way, but through the rasterization way, which means that we are going to first basically project all the splats into the image plane and do some calculation. So basically what we are doing is that it's kind of the same in terms of the, for each of the pixel, and also when you consider some kind of ray that we are shooting from the camera center to each of the pixel in the image plane, basically we're gonna collect all the ellipsoidal, the Gaussian splats that are basically where the rays are basically passing through. And then we are going to sort them, sort all the Gaussian splats along that ray from the closest to the farthest. And let's consider that we are having some kind of index with all the Gaussian splats that are basically where the rays are basically passing through with the index of the I here. And then we're gonna basically calculate the Gaussian corner in the ray coordinate system, which means that we are calculating the P double prime and the V double prime, and also the Jacobian matrix in terms of that we also calculate the scaling term here. So actually, there should be some kind of the So this is the Gaussian corner defined in the ray coordinate system, which is basically also can be represented as the Gaussian split, the corner in the object coordinates, and it's kind of the rotated and the scaled version, right? And then once we collect all the Gaussian corners defined for each of the Gaussian splits, we are going to basically now compute the volume rendering equation. And also in our the volume rendering equation, now we're going to consider that the opacity, the term is defined like this. So the opacity term is basically defined as some kind of the opacity for each of the split, and which is like weighted by the Gaussian corner here. So based on the quarry point that we are having over the ray, we are basically determining the weight for each of these split. And then the final, the opacity is now calculated as the weighted sum of the opacity for each of the Gaussian split. And also the multiplication of the color and the opacity is also defined in this way. So we are simply basically multiplying the color here and taking the weighted sum, which weight is now defined based on the Gaussian color. Clear? And based on that, so now we are going to see how we can calculate the volume rendering the equation. And before getting into that, but we are going to use some kind of the one strong assumption, which is about the non-overlapping the local supports, basically, which means that basically we are basically determining the weight for each of the split as kind of the Gaussian the corner, right? Which will never become zero, but which can get closer to zero, right? Depending on the position of the query point in the 3D space. So what we are going to assume is that those kind of the Gaussian splits are distributed in the 3D space in a way that there is no some kind of some big overlap across the splits, which means that when the weight defined with the Gaussian corner in the one split is having some kind of the non-zero weight, we're going to assume that weight coming from the other split is very close to zero. Obviously, it's very strong the assumption. It really depends on like how those kind of splits are basically distributed in the 3D space. But we are going to use this kind of the assumption to simplify the computation. Make sense? Any questions on this? So based on that, basically how we can compute the volume density equation is basically nothing. But this was basically the equation that we have seen, right? The volume density equation. And the transparency was defined in this way. Then now what we can do is that we are basically simply replacing this term with the definition of the opacity and the multiplication with these two defined with these splits as we have seen in the previous slide, right? Replacing this part and this part. The only change that we are making in the transparency term here is that based on the non-overlapping the support the assumption, what we are going to do is that when you basically consider applying calculating this kind of opacity and the color with each of the Gaussian split here, the sorted the Gaussian split here. So for example, like if we compute those terms with the each of the ith the Gaussian display term, we are going to consider only the split that are basically in front of that specific the Gaussian split. Because like the splits that are in front of each of the split will be only some kind of the Gaussian develops that will affect in terms of computing the transparency, right? So from here to here, what we are doing is that while we are taking the integral over the transparency term here for the entire range of the ray, we only consider some of the corners that are basically in front of each of the Gaussian corner in terms of that, those are basically the corners that will determine the transparency. Then after this kind of conversion, what we can say is that we are also taking out the summation here out of the exponential term here. So the summation here becomes the product out of the exponential term here. And we can also take out the whole terms out of the summation like this. So we are basically having this kind of the formulation. So yeah, you can check out some more details, like how we are making some changes of the formulation based on some assumption here. And you can see like what's the kind of good thing of like this formulation. So after we are making this kind of the change, can we simplify this equation with this kind of like two things? So let's say like we can now compute some kind of integral of the Gaussian corner along some kind of the direction here. So let's basically replace this term as kind of the qi here. So just introducing kind of new notation. And then to simplify the computation, we are also going to use some kind of the linear approximation for the exponential term here as well. So we are going to replace the exponential term here as kind of the 1 minus x, which is also using the Taylor expansion. So based on this kind of the things here, can you also simplify this equation? So I basically recommend you to do your own hands-on work for this. And then we will see that actually after using those kind of the two kind of things like approximation and the new terms, what we can see is that actually those like whole equation can be simplified in this way, just like replacing the integral term here into the qi here, and just replacing the exponential as kind of the 1 minus x here. So you can say that actually the whole equation can be simplified in this way. So after like converting everything into in this way, then you can see that actually this looks like quite simple in terms of that for each of the I. So this whole the term becomes our the transparency, right? So this term becomes the transparency, and then we are not doing nothing but basically multiplying some kind of the color and the opacity and some kind of the weights that are defined with the Gaussian the corners. So here the remaining question is that how we can take the compute the integral here. So this integral was basically doing some taking the integral in the ray coordinate system, right? So what we can see is that this is actually the Gaussian corner which is now defined in the ray coordinate system. And taking the integral here basically means that we are also taking the integral along the ray, right? And in the ray coordinate system, the distance along the ray was represented as the third coordinates, right? So we are having the x and the projected x coordinates and the y coordinates. Those are determining the position of the ray in the image plane. And the third coordinate is basically representing the distance along the ray. And what we are basically calculating here is basically taking the integral along the distance along the ray. So actually this was nothing but we are taking the integral along the third coordinates of the ray coordinates. You can see the meaning of that. So when I just like use the t here, actually the t was basically the third coordinates of the ray coordinate system. So actually here what we can see is that when you have some kind of the Gaussian corner defined in this 3D space, what will be kind of the output when you take the integral of that Gaussian the corner along like one of the specific the axis in the coordinate system. So here specifically we are taking integral along the third the coordinates, the z axis in that coordinate system. So the good thing of that is that when you take the integral of the Gaussian corner along the one of the axis in the z coordinates, specifically in this case, then actually what we can see is that becomes the same. That we are just simply calculating the 2D Gaussian. So you can see that actually this is nothing but we are taking the projection of the some 3D Gaussian with some kind of the one of the axis in this space, and taking integral along that. So that is basically becomes identical with calculating the 2D Gaussian. So now we can see like why we want to basically approximate the 3D, the Gaussian, the corner with some kind of like representing the Gaussian corner in the ray coordinate system. Actually, the reason for that is that we wanted to basically compute the integral of the Gaussian corner to be simple as possible, as much as possible, but just it becomes just the 2D Gaussian, the computation. So that's basically the thing. What we do is that we represent like all the Gaussian corners in the ray coordinate system and calculate the volume rendering equation. And the main part in the volume rendering equation will be basically taking the integral of the Gaussian corner, which actually becomes like computing the 2D Gaussian in the space. So that was kind of the basic idea in terms of how we can do some kind of the rendering with the 3D Gaussian split and also with the volume rendering equation. So there are some kind of some complicated things in terms of the formulations. I recommend you to check out those kind of some formulations after the lecture. And on Wednesday, I'm going to briefly mention about basically how we can also do some kind of the training with the Gaussian split and how we can basically also expand the Gaussian split in terms of like reconstructing the 3D scenes. And then actually we can see that actually the reconstructed 3D scenes with the split can be rendered in this way. So we're gonna wrap up the Gaussian split next Wednesday, and then we're gonna have some summary for the midterm. Okay. Any questions on this? So as I mentioned at the very beginning, we're gonna make the Wednesday session as the offline session, as the so in-person session, which will be happening in the N1 room 201. I'm going to see you next Wednesday. Okay? Yeah. Thank you. If you have any other questions, please post the questions on Slack. Thank you. Bye.
Thank you.